Now, when we talk about jointly distributed random variables, we're actually talking about more than one variable, as in the variables. So we have at least two variables that are distributed together. Okay, they are actually their PDF or PMF or CDF or whichever function we are writing is written together with both of them, at least both of them in the picture. Now, we will start with the CDF, and then we will go into PMF and PDF as well. Now, when we talk about CDF, we already know that we are talking about the capital F, which is the probability of up to a limit from minus infinity to A, for example. The sum of that, all probabilities in that interval. Now, when we talk about joint CDF, joint distribution, we are talking about two, at least two, but in most cases for us, it's going to be two here, of two different variables like X and Y that are being distributed together. So we have two upper limits instead of one now, A and B. A is for X and B is for Y. So as you can see, when we write FAB, we are actually talking about the probability of X is being less than or equal to A, and Y is being less than or equal to B together at the same time. Now, we have this joint distribution, but we still have our marginal distributions, the distributions of the variables by themselves. So we can talk about the marginal distribution of X, which is Fxa, which means that the probability of X being less than or equal to A at all times. So this actually comes from the joint distribution as well. We can just replace B with infinity and we will see that, okay, this is for all values of Y. When you say Y is less than infinity, okay, all values of Y. So it's just for X. If it's about all values of Y, it doesn't really, affect X at that moment. So we can just say that Fxa, the marginal of X, marginal distribution of X is equal to A infinity, the distribution, joint distribution of X and Y with A infinity parameters. Same for Y, of course. Doesn't really change when you change the variable. We can also say that all joint probability statements for X and Y can be given in terms of their joint distribution function. Now, for example, if we talk about X being greater than A and Y being greater than B, probability of X being greater than A and Y being greater than B at the same moment, we can just write this like this. Okay, we can just say it's the complementary, 1 minus the complementary, and then we can open up the complementary and see that it's just, instead of the intersection, it's a union. So we have this union here, and as you can see, we have two complementaries inside the parentheses right now. We can just open these up as well. Instead of being X greater than A, we can just say X is less than or equal to A. So from this union, we know that this is a union of two sets. You can think of it as two sets. So we're just gonna write the set formula for that one. So the first one plus the second one minus their intersection. Now this intersection is actually the joint probability, the CDF for X and Y together. So we can just write all of this in form of the cumulative distribution function. So this is actually Fxa, and this is Fyb, and this is X and Y together, so Fab. So we can just write all of these like this. So this probability statement can be written in this form as well. So this will be equal to this one. We can just use the joint probability CDF function to state all the similar probability statements. Now we have the joint PMF as well. The PMF part, as you can remember, was for the discrete random variables. Now if we have two discrete random variables jointly distributed, we can see a joint PMF in here. So this joint PMF is written like this. As you can see, this is just two different distributions, two different random variables getting a value together. So we are looking for the probability where X is equal to X and Y is equal to Y at the same time. If these were two different, if these weren't distributed jointly, you could just check them one by one, but they are distributed jointly, so you have to check them at the same time together. But also we have marginal distributions in here as well. Marginal PMFs, actually, marginal mass functions. The marginal mass functions for x and y can be found by removing the other variable from the joint PMF. The removal part is done by summation in discrete and integration in continuous. You'll see it when we get there. But in here, to get the PMF of x, the marginal PMF of x, we have to remove y. So we have to sum all values of y, just keeping the x constant at a value. You will see what I'm talking about in the example in the next slide, but still this summation gives us the margin of x. Let's start with the example and you'll see what I'm talking about. Well, we have 3 balls that we are going to choose randomly out of an urn which contains 3 red, 4 white, and 5 blue balls. So we have a total of 12 balls. We're going to pick 3 of them. And now we say, if we let x and y denote respectively the number of red and white balls chosen. So x is equal to number of red balls and y is equal to number of white balls chosen from those 3 balls. Find the joint probability mass function of x and y. Now, the joint probability of x and y is x is equal to I and y is equal to j. So these I and j values, what can they be? We know that there can be at least 0 because we may pick 0 white or 0 red balls, and they can at most be 3 because we can pick at most 3 balls. So all 3 of them can be red or all 3 of them can be white. So both I and j values can be anything between 0 and 3, 0, 1, 2, 3, any of those 4 values. We also know that our total number of balls is 3. So I plus j cannot be greater than 3. It must be less than or equal to 3. So we know that I and j can be 0, 1, 2, 3, and their sum can be at most 3 as well. So the sum can be 0, 1, 2, 3 as well. We also have a third variable here, which we are not going to talk about, the z variable. This is the number of blue balls. We don't need it though, because we already know what's going to happen from I and j. Anything that's left to z will be 3 minus I minus j anyway. So we don't need to talk about it here. We're just going to focus on x and y. So what about I and j values? For example, I can be 0, no red balls picked. So j can be 0, 1, 2, 3. All of them is possible. When I is 1, j can be 0, 1, and 2 only. It cannot be 3 because the sum will be 4, which is not possible. When I is 2, j only becomes 0 or 1. And when I is 3, j can only be 0. So we have a total of 10, I think, different combinations to find out. So here, let's start with all of them. We have 0 and 0, 0 and 1, 0 and 2. It goes on like this. We just focus a few of them and we will remember how we will do those. So 0 and 0, it means that I is 0 and j is 0. So z value is 3. We have 3 balls. We don't have any red or white balls. We're going to pick 3 balls. So we have 5 balls and we pick 3 out of them, 3 or 5. And now we're going to 5 choose 3, and then we're going to pick 3 balls out of 12 balls for the whole sample space, so it's 12 choose 3. And this division gives us the probability for picking 3 blue balls out of 12 balls. So for 0 and 1, this means that we don't pick any red balls but just 1 white ball and 2 blue balls. So this is going to be 5 choose 2 for the blue balls and 4 choose 1 for the white ball out of 12 choose 3 whole sample space. So it's 40 over 220. And this goes on like this. Now, when we calculate everything, and I think we are missing 2, 1. Yes, there should be P2, 1 as well, but still we're going to be calculating them in the next page anyway. So we get the PMF, but we can also show the PMF as a table, which is more, logical and easier to analyze, because in this table, as you can see, these values are all the values that were calculated in the previous slide. So it's I is 0, j is 0. This one was the probability. I is 0, j is 1. This is the probability, and etc. So in here, in this table, each row corresponds to a value of x. So this is x is 0, I becomes 0. This is x is 1, this is x is 2, and this is x is 3. Now, when we talked about marginal PMFs, we said that we should sum for all y values. So when I'm looking for x is equal to 0, the margin of x at the value 0, I have to sum every value of 0 for that row. So we're going to sum these 4 values, and we're going to get 84 over 220. This is the probability for x is equal to 0. The same can be done in all other rows as well. We're just going to sum this row to get the marginal PMF for x is equal to 1, and sum this row to get x equal to 2, the probability of x equal to 2, and sum this row to get the probability of x equal to 3. So as you can see, all these values inside, sum up to 1. So do these values sum up to 1. So this is expected anyway. Now, here, these are the marginal PMF of x values. And the ones over here on the bottom, these are actually the sums of those columns. So this one is y is equal to 0. The sum is the probability of y is equal to 0. This one is y is equal to 1. So the sum here is equal to the probability of y is equal to 1, etc. So this one is also the marginal PMF for y. Continuing on like this, we have the continuous, joint PDFs. Now, the main difference is instead of summation, we get integration. And we're going to use intervals instead of values to, calculate the probability values. Now, as you can see here, x and y are continuous, jointly continuous, and they can be written like this: the fxy. This is the joint PDF for x and y. The fx and y can be written like this. So we're just going to say that to find the probability of xy being inside a set C. Okay, this can be any 2 intervals. We can just find them in different ways, and we will see in the examples later on. But still, for any set C, we can just find the probability by taking the double integral of x and y. Now, this double integral is very, very important in this chapter, because you're going to see it, prominently, and we have to be able to take this double integral perfectly. Because you usually have problems with it, so I advise you to, study double integral before studying this chapter, so that you can, freshen up on your math skills. And this double integral will be very important because the calculation part is purely on integral in this, chapter, if it's continuous we're talking about, and most of those integrals will be double integrals. Some of them will even be triple integrals. Very, very, little percentage, but still there can be triple integrals in there as well, which is going to be hard, and so you have to brush up on your, math skills. Now, as you can see, we have this formula, this double integral, to calculate the probability. So if the intervals are different and they are not related to each other, we can just write if that x is equal is inside A and y is inside B. So I can just say that A is the limits upper and lower limits for x, and B is the upper and lower limits for y in this integral anyway. So I can just write it like this as well. And now we have the cumulative distribution function, which is going to be written in this way. As you can see, x is in the interval from -infinity to A, and y is in the interval from -infinity to B. We already know these from chapter 5. So instead of one integral, we have again 2 integrals, a double integral here. So from -infinity to B, from -infinity to A. As you can see, these are the, okay, this 2 is wrong. B should be here and A should be here, but still we get the gist of it. So we have 2 integrals instead of 1. Okay, what about marginal PDFs? Just like marginal PMFs, they are just a summation, but the summation is done here with the integral. So when we're looking for the marginal PDF of x, we have to take the integral of the joint PDF for y, so that we can get rid of y. When we take the integral for y, we are just summing all values of y, so we are getting rid of the y. So we have only x left. When we want to find the marginal PDF of y, we have to integrate everything over x. So we get rid of the x and there's only y left. We will see how this is done in the example here. Now, this joint transfer function has two parts. The upper part, as you can see, is for x from 0 to infinity and y from 0 to infinity, and it's equal to 2 times e to the power of minus x and e to the power of minus 2y. Now, this part is the positive part, and we have 0 otherwise. It's not really that important. But as you can see here, we are given the joint PDF. This is our joint PDF, and we are given the intervals, the limits, upper and lower limits of it. So from here, it's asking us to calculate the probability of x being greater than 1 and y being less than 1 at the same moment, at the same time. So to be able to calculate this, all we have to do is just take the integral. And this integral will be taken from 1 to infinity for x and from 0 to 1 for y. So when we take this integral, as you can see, this integral might take a bit of time, a few minutes to take, but still we will get this equation in the end. On the other hand, this is a bit more trickier. There is the probability expression, but the x is less than y. Probability of x being less than y. Now, this is not like x is greater than 1 and y is less than 1. This is just having x being dependent on y. X is less than y. Now, to find the limits, the upper and lower limits in these kind of questions, we have to, graph, if we can, we have to graph the limits, so that we can find the integral area. Now, this one, x is less than y. Now, to find this one, we have to graph the equality first, then we can find the inequality. To find x is less than y, we have to graph x is equal to y, which is over here somewhere, x is equal to y. Now, in this one, x is less than y. Now, when we are talking about x is less than y, we are talking about, let's do it like this. We are talking about this part, okay? This part over here. Now, with this one, all values over here, x is less than y for all values over here, for all points over here. For example, if we take any part over here, we know that, for example, over here, x can be 1 and y can be 5, for example. So x is less than y all the time. Y can go up to infinity over here, but x is stuck with 1 over here. So x is less than y. It's the same for all those values. So when we take a look at here, we also have two more, limits, two more constraints for us, which is actually x is greater than 0 and less than infinity, of course, and y is greater than 0 and less than infinity. So our integral area is actually this part over here now, and goes to infinity, of course. Now, in this integral part, we have to take the integrals for x is less than y and these two limits as well, okay? These two constraints as well. Now, to be able to take this integral, we have to find the upper and lower limits for that integral. And to do that, we have to, the easiest way to do that is just, sorry. To do that is just to take an arrow and draw an arrow parallel to one of the, axes. And we pick which axis we want to do that. And I'll start with the x one. So I'm just gonna draw an arrow parallel to x. Now, I don't like the color. Just do it like this. Now, this arrow enters our integral area from one point and exits at another. So I keep drawing other arrows, so it's obvious. It always enters at the same line and exits at the same line. So this entering line will be my lower limit for x, because these arrows are parallel to x, and the line over here that the arrows exit will be my upper limit for this x. So x is greater than 0 and x is less than y. So from 0 to y, x is going to be integrated from 0 to y. Other than that, for the second variable, for y, all we have to do is just find the constant values, the lowest and the highest constant values that it takes, the scalar values that it can take, which is 0 and infinity. So this integral will be from 0 to y for x and 0 to infinity for y. As you can see, let's just clear these. 0 to y for x and 0 to infinity for y. We could have done this in a different way. We could have started with y instead of starting with x. Then it would be from y to infinity, sorry, x to infinity for y and 0 to infinity for x anyways. This integral, after a few, lines, like at least 4 or 5 lines maybe, because it's going to take 2 or 3 integrals in a chain to be able to solve this one, it's going to give you 1/3. Now, on the last one, the last part, C part, it's asking us the probability of x being less than a. Now, this is the marginal probability. We don't have any y values here, so it can be all y values. So I have to get rid of y. So all I have to do is just take y and integrate it from 0 to infinity, and then take x and integrate it from 0 to a. Now, as you can see, this is exactly what we have done. We are starting with y. We have always started with x, but now we are starting with y because we have to get rid of y to find the margin of x. So we are starting with y and integrating it from 0 to infinity, and then this part will yield us the margin of x. After this margin of x, all we have to do is just find the probability for x being less than a by taking the integral from 0 to a. So it will yield this one. Again, this one takes a few lines of integrals to yield that equation. Another example. Now, this is a bit more symmetric because x and y values are here together at the same time. They don't have any different constants or anything else. And both x and y is between 0 and infinity. But the question being asked is, find the density function of the random variable x over y. Now, we have already found, density functions for different, singular variables. For example, we were talking about y is equal to x squared. We already knew x, so we would be trying to find the density function of y is equal to x squared. It's actually the same thing here. We already know the joint PDF, and we are trying to find some different, representation of those variables instead of using the joint PDF itself. So what we need to do is, when we want to find the density function of random variable x over y, we have to start with the joint distribution function, the capital F, because we already know that it's going to be the probability of x over y being less than a, something like less than or equal to a. So we start there. This one, the joint distribution function of x over y. Now, this one comes from here. X over y is less than or equal to a. And we can just leave x here alone and say that x is less than or equal to ay. Then what we need to do is x is less than or equal to ay is just can be calculated from this joint distribution, joint density function anyway. So what we have to do is just take those x values, okay, integrate x from 0 to ay, because the upper limit is ay now. X is less than or equal to ay, and the lower limit is 0 anyway. And y is going to be from 0 to infinity. Again, we can graph and make sure that these are like this to see, the limits are like this, but we haven't graphed it here, so you can do it as a homework, I guess. But try to graph as much as you can so you understand how those, limits, upper and lower limits are found. So this is actually an easy one because it's the same from here, the limits from here, but still it can change. So you have to graph, you have to get used to graphing those things. So from a to 0 to a1, we are going to integrate dx, and then we're going to get this one. And after getting this one, we're going to have to integrate this from 0 to infinity for y, and this is going to be the capital F, our CDF, cumulative distribution function for x over y. But it's asking us the density function, so what we need to do is just take the derivative, and we're going to get this one. Now, this is exactly the same, method we have seen in the 5th chapter. So we are using the same method. Nothing has changed here. The only change is we need double integrals now. So we have to find, you know, the upper and lower limits and do it from there. What about another example? Now we have C value here in fx, an unknown value. We have to calculate this C value first, and it's asking us to find it anyway in A. So how can we find the C value? What we need to do is we need to find upper and lower limits for the integrals and double, you know, integral this joint probability density function and make it equal to 1. Now, as you can see in here, there's a little snag. X is between minus y and y. So x is between minus y and y. We have to graph this one to be able to understand it fully. Now, let's start with this one. We are going to write the x's, x and y. And now we're going to put down our x is equal to y. This is x is equal to y for this part. And we need minus y is equal to x, which is this one. Now, what we need to do is find this area. Where is this area? And that's going to be for y is greater than 0. So we are looking for this area in somewhere over here, because y is greater than 0. We know this. And so we cannot take the bottom, because the bottom part is y is less than 0. And we are looking for the x being between these two values. Now, start with this one. X is less than y. X is less than y is the area above this line over here. And minus y is less than x. Now, minus y is less than x is over here. And the intersection of these two parts gives us this one. Now, we can just undo this and say that, okay, this part is what we are looking for over here, etc. So this is our integral area, this, you know, infinite triangle. Now, in this triangle, we have to find the value of C. So I will start in a simple way. I will start with, let's start with X. So what I have to do is just draw a line parallel to X. Okay, another line parallel to X, another line parallel to X. So as you can see, these lines are entering my integral area from this line and exiting from this line. So this line is going to be my lower limit, and this line is going to be my upper limit. This line is minus y, and this line is y. So my x is going to be integrated from minus y to y. And then I'm going to integrate y from 0 to infinity, because it can take values of 0 and infinity. So, as you can see, it starts with, let's clear this one. It starts with finding the margin of y. So it's going to integrate for x from minus y to y. It's doing this like this to be able to, you know, find the marginal for part B anyway. So we can just write double integrals over here as well. It doesn't really matter to find the C value, and then you can just find all the marginals later on. But we can start like this too. So this is the margin of y, the margin of y. When I integrate this for y from 0 to infinity, I'm going to get 1. So I just integrate it and make it equal to 1. And after 3 or, I don't know, 4 different integrals, it's going to take long. We get the value of 1 over 8 for C. Now, as I have found C, I can just write C in here and find the marginal density of Fy immediately. And then what I have to do is just write C value over here, 1 over 8 over here, and integrate this in, you know, for y, so that I can find the margin of x. So as you can see, let's just draw this one once more, because it is important. Now, I had these 2 parts. I'm not a good drawer, but still, we already know that this is our integral area. Now, what I want to do is integrate for y. So when I'm integrating for y, I have to just draw lines parallel to y. As you can see, I'm entering from 2 different lines and exiting from infinity. So I can just say, okay, I'm going to take this line where x is less than 0. So I'm going to write this integral. And then I'm going to take this line where x is greater than 0, and I'm going to write this integral. We can write 2 different integrals, or we can just say, okay, these two lines are actually forming a function, and this function is the absolute value of x. So I can just write from absolute x to infinity. I can do it both ways, okay? I can write from absolute x to infinity, or I can just write two different integrals, one for this part and one for this part. They will give the same result anyway. So we get this one. Now, what if we have more than two variables, two random variables? We can have 3, 4, 5, and infinitely many number of random variables together. Not infinitely, but still a lot of random variables together. Now, when we have this many random variables, it's just gonna keep increasing the number of integrals we have to take. That's it. So the more variables we have, the more integrals we have to take. But in this class, we're not gonna have to take anything more than 3 variables, so nothing more than a triple integrals, hopefully, because even triple integrals are very hard, at least to tackle during an exam. So what you're going to see mostly will be two, double integrals, two variables and double integrals. There are some exceptions you will see here in the examples, but still, most of the time, if we are dealing with integrals, it's going to be double integrals and not triple most of the time. And anything above triple, a definite no. You won't see them in this class or exam. So there is the multinomial distribution. This is actually something we already know from the first and second chapters. We're just naming it here. This is for trials, experiments with independent identical values. We have lots of different, we are making experiments and we have lots of different results from them. For example, we are rolling a die, we can get 1, 2, 3, 4, 5, or 6. So we just keep rolling that die a lot of times. So we are making lots of different experiments, but still it's the same experiment, identical experiment, the rolling of the 6-sided fair die. Now, what you see here, this formula will be, will look like to be a bit complex at first, but I'm just skipping the formula and showing it in the example, which is going to be extremely clear for you, because as I said, this is something from the first and second chapters you're going to remember, even the fourth chapter, but still. We are rolling a fair die 9 times, okay? What we want is for 1 to appear 3 times, 2 and 3 to appear twice, and 4 and 5 to appear just once. And we don't want to see 6 at all. So, what's the probability of rolling 1 3 times? Okay, 1 over 6, 1 over 6, 1 over 6. That's it. 1 over 6 to the cubed, and 1 over 6 to the power of 3. So, okay, we just have this one in the back. What about rolling 2 twice? Okay, 1 over 6 times 1 over 6, so square of 1 over 6. What about 3 2 times? Again, 1 over 6 square. What about rolling 4 just once? 1 over 6. What about rolling 5 just once? 1 over 6 to the power of 1. What about not rolling 6 at all? Okay, we don't need to look at this. 1 over 6 to the power of 0, which is 1. So we already know the probabilities for these actions, but we don't know when these actions are happening. Okay, am I rolling the ones at the first 3 times or the last 3 times, or are they spread in between 2, 5, 7, etc.? We have to check each one of them. So normally for 9 experiments we have 9 factorial different ways of doing those, but some of these outcomes are the same. For example, 1 comes up 3 times, so it doesn't matter which one is which. You can just eliminate these 3 times, which is 3 factorial. So you have to eliminate 2s and 3s as well, which are 2 and 2 factorial together. So as you can see, these are our orderings, and these are our same orderings which have to be removed. So these are the all the different probability values we have calculated, and this multiplication will give us this value, which is the multinomial distribution actually. But we already know this one. This is just permutation, where we have to remove those duplicates, and these are just the these over here are just the probability values for each one of the experiment outcomes. So we can just write these without this formula as well, but this formula this formula over here, is just the same thing. As you can see, these are the orderings, these are the, duplicates, and over here, these are all the different probability values. And it's written like this over here for this question. Now, we have independent random variables, just like in, independent events and stuff like that we have seen before. Those independent random variables in a joint, distribution, they can be, well, they can be written apart from each other. You know what I'm saying? You remember the independent events A and B, they can be written as the intersection, the probability of their intersection can also be written as their, respective probabilities multiplied. It's the same over here. So we have X and Y random variables. On those random variables, their probability together, the intersecting probability, the joint probability can be written like this. But if they are independent, the X and Y random variables are independent, then they can be written apart as well. These are going to be the same values anyway. This is true for the distribution. This is true for the density or mass functions as well. Now, as you can see, this is a binomial, two binomial random variables. These are two random binomial random variables, and they have N and M trials, independent trials, and they all have a success rate of P. So their let's say their joint PMF together is written like this, which is also the same as the marginal PMFs, their marginal PMFs, that's a multiplication of their marginal PMFs. It's going to be the same thing because they're independent. If they weren't independent, then you couldn't have written it like this. You would have to find another way of writing those things. Now, a simple example for that one. A man and a woman decide to meet at a certain location. If each of them independently arrives at a time uniformly distributed between 12 noon and 1 p.m., find the probability that the first to arrive has to wait longer than 10 minutes. Now, we are talking about a 60-minute interval here from 12 to 1. So we're gonna just assume that we are talking about 0 to 60 in minutes instead of 12 to 1, because it's already asking us the question with minutes, 10 minutes. So it's easier to transform into minutes. So our arrival for both of them, their arrivals, are uniformly distributed between 0 to 60 in minutes. Now, it's asking us to find the probability that one of them doesn't wait for the other more than 10 minutes. Now, this can be either of them. It doesn't really matter which one is which. So let's assume that the first one to come is, let's say, X, and the second one is going to be Y. So if X is the first one to come, then his 10 minutes, he's gonna be waiting for 10 minutes at most. This is the probability we are looking for, which means that Y should be less than X plus 10. Okay, and otherwise, X will have waited more than 10 minutes. It's the one coming first. So you can just think of like this: when you're waiting for it's actually asking us to wait longer than 10 minutes. Sorry, okay, wait longer than 10 minutes, not wait. Then it's the opposite side. Then we have to assume that he's gonna wait more than 10 minutes. Why? The second one coming is gonna wait more than 10 minutes. So it's gonna have to greater than X plus 10. So if it has to wait more than 10 minutes, then it has to be greater than X plus 10. So X plus 10 is gonna be smaller than Y. This is our, limit. This is the, line we are looking for. Now, we also know that X and Y are both between 0 and 60. And the other way around, if Y comes first, then X is going to have to wait more than 10 minutes. So Y plus 10 is going to be less than X as well. These two different constraints, they're symmetric. If one of them has a probability P, then the other one has a probability P as well, because you can change the people around, it doesn't really matter. So what we have to do is just calculate one of these two probabilities and just multiply it by 2. To do that, we'll pick one. In here, I think we have picked X plus 10 is less than Y. So X is coming at the time and Y is gonna wait more than, he's gonna wait more than 10 minutes for Y to arrive. So in here, this, I'm sorry. In here, this part, what we need to do is just draw. Let's start by drawing it like this. Now these are the axes. Now I know that this one here, x plus 10, is less than y. So if we just start with treating this as an equal. So if x was equal to 0, then y would be equal to 10. So the line is over here somewhere. So it's going to be going like this. This line is x plus 10 is equal to y. We also know that we have this one and this one is writing right, 60 and 60. Now, as you can see over here, we are looking for x plus 10 is greater than y. The area we are looking for means that, sorry, less than y, means that x can be less than y. So over here somewhere. Because it's gonna be, limited by y is less than 60 as well, which is this one, and x is greater than 0, which is this one. So this area is our integral area. Now, in this area, we're gonna have to find the, upper and lower limits. To find that, we have to pick which one we are starting first. So let's assume that we are starting with, I don't know, x first. So if we're gonna start with x first, then I'm gonna have to, draw parallels to x and check where those arrows enter our, integration area, which is this one, which is x is equal to 0. And it exits over here, which is x is equal to y minus 10. So we enter here, we exit here, so we are going from 0 to y minus 10, as you can see, 0 to y minus 10. And then for y, we have to check the, smallest and greatest values. The smallest value y can have in this triangle over here is 10, this point, and it's 60 at most, so it's from 10 to 60. As you can see, this is not from 0 to 60, it's 10 to 60. Although y is, both y and x are situated, located between 0 and 60, the real limit, the real, lower limit is 10, not 0, because this area is allowing y to be 10 at least, okay? Any value over that is going to be, taken into account anyway. So it's from 10 to 60. Now, when we take this integral, as you can see, it's 1 over 60 squared. Why is that 1 over 60 squared? Because our interval is from 0 to 60. So our PDF is 1 over 60 for both of them, for x and y together. And they're independent, so their joint probability is their multiplication, which is 1 over 60 squared. So this is the joint probability, 1 over 60 squared. And we just take this integral and we find 25 over 36. Now, this 25 over 36 is the, whole probability, which was multiplied by 2 to find both of these sides. So we're just going to be, done with it like this one. So there is also another point for independent random variables. We may not always be told that two variables are independent, but we can still understand that from looking at their joint probability, joint distribution or joint density function. Now, in here is the joint density function. Now, as you can see, if we have this density function, this PDF, joint PDF, which is made of x and y, and if we can factor this function into two different functions, where one of them is only made up of x and the other one is only made up of y, values of y, then, and of course, if the limits or constraints are independent and they can be taken apart as well, then we can say that these x and y random variables are independent from each other. So what we need to do is check if we can factor this, joint PDF or PMF, depends on the random variables. If we can factor those into two different parts, which one of them is only made up of x's and the other one is only made up of y's, then we can say that it's independent as long as the upper and lower limits can be, you know, factored as well. They can be separated as well. Here's an example, two examples actually. The first one is over here, 6 times e to the power of 2x and e to the power of minus 3y. Now, as you can see here, the x and y components can be separated. I can even, you know, separate 6 into 2 parts like 2 and 3, 6 and 1, etc. I don't really care. But the most important part is over here. X and y can be separated and written as multiplications. So this one can be independent as long as the constraints allow it, okay? Those limits allow it. Let's see, 0 to infinity for x, 0 to infinity for y. X and y are independent here as well. They don't, you know, limit each other. So yeah, this is actually, these two are actually independent random variables. No questions. But in the second example, as you can see, 24xy, this can be factored into x and y as well. 4x, 6y, 3x, 8y, I don't care. You can just, you know, factor it into easily. But over here, we have x plus y is between 0 and 1. Now, this one cannot be factored or separated. So x and y are actually affecting each other. If one of them, you know, grows, the other one has to diminish. So these two are affecting each other, so they cannot be independent, plain and simple. Now, here's an example for independent and triple integration, independency and triple integration. Let x, y, and z be independent and uniform distributed over 0, 1. Okay, they are uniform over 0 to 1, so their f, their density function is 1 for all of them, for each of them. So compute the probability that x is greater than y times z. Now, this one, we have to graph it normally, but in here, it's actually easy to, you know, visualize it. Now, we have x, y, and z, think in three-dimensional, and they are all, you know, limited by from 0 to 1. So there's a, you know, cube there. We have a cube there, which, you know, has all the, you know, all the lengths with 1. We have a cube there. Now, in this cube, x is greater than y times z. Now, we can write y times z as a, you know, plane. So not a real plane, but something curved. So in this curve, we are looking for the value of x being y times z. And y times z is going to be between 0 and 1 anyway, because y and z are between 0 and 1. So y times z is going to be between 0 and 1 anyway. So there's not going to be any limits changing there. And you can see it, you can visualize it like a bell, I think, in the, you know, third dimension. But still, this x is greater than y and z is going to be giving us the only limit we need. And this is going to be the lower limit for x, which is y times z. All the other limits are 0 and 1. So as you can see, when we take the triple integral, and we say x, we start with x. X is going to start from y times z, and it's going to end with 1. Both y and z are going to be from 0 to 1. This integral, with these values being just 1 over here. So we have this one. This is the first integral at the end of the first integral. This is the second integral, and this is at the end of the third integral. This is actually a very easy integral once you write these, you know, limits correctly. So what we have here is a simple triple integral. We're gonna see stuff like this sometimes, simple triple integrals, maybe in the exam too, but most likely it's gonna be hard double integrals instead of simple triples. We'll see. And now we have the sum of independent variables. Now this part is actually very, you know, useful and it's important, but what you need to know is just the final, you know, equation, this one. The other ones, the points leading up to that is just a good exercise, good mathematical exercise for, you know, integration and for differentiation. You should check this out, but you need to know this by heart at the end of the day. But as the exam is going to be open book, it's going to be easy to, you know, check this out anyway. Now, this is talking about a convolution. A convolution is the, you know, summation of two different or maybe similar variables, random variables, x plus y. Now, as you can see, these two independent random variables, independence is important, these two independent random variables can be added together. So when we add them together, we are just looking for the, you know, PDF of this, joint PDF of this addition, summation. It starts with the cumulative distribution function as usual. We usually start with CDF to find the PDF, and then we differentiate. You can remember that from, you know, previous class, I think. Now, x plus y. This is the probability we are looking for. We will just integrate it, and then we will find, when we simplify stuff, we're going to find this one at 10. Now, this is the cumulative distribution function. What we need is the density function, so we just differentiate this one, and this is the variable a, so we differentiate it for a, and we get this one at 10. Now, this here is the PDF, joint PDF for summation x plus y. This is the same, this is true, this is also true for every summation, okay? Independent random variables at least. Now, we're going to use this one in the example. Now, we have two uniform distributions that are distributed on 0 to 1, okay? So their f is 1, simple enough. And we're looking for x plus y. Now, when we are looking for x plus y, we know that x plus y is going to be between 0 and 2, because x and y are between 0 and 1. So x plus y has to be between 0 and 2. We don't know which is which has the more, probability, etc. But we know that the summation is going to be between 0 and 2. Now, we also know that both of these x and y marginals are equal to 1 when they are between 0 and 1. When the k value, when this parameter is between 0 and 1, this variable is between 0 and 1, the function is equal to 1, and it's 0 otherwise. Now, let's go back a bit. This one here, we're going to use this one, okay, this formula. And in this formula, we have fxa minus y and fyy. We already know that fyy is 1, okay, because we know it here. It's 1 when it's between 0 and 1. So we're going to assume that it's between 0 and 1 anyway. Y is between 0 and 1 anyway. So it's 1. Over here, though, the second part or the first part, how we look at it, is still there. So it's going to be, have to integrate it from t0 to 1, fx a minus y dy. Now, this a minus y is going to define the value for f. Think of it like this. Let this be a value, I don't know, k, like this one here. As long as this k, this a minus y is k, this k is between 0 and 1, this function will yield the result 1. But if this k is greater than 1 or less than, smaller than 0, then it's going to yield 0. So I have to make sure that this a minus y is between 0 and 1. As long as this holds, then I'll be happy, no problems there. But to do that, I have to figure out if a is greater than y or not. Because if a is less than y, this is automatically negative, and it's going to give us a 0 value. So we have to check this one. A can be anything between 0 and 2, because we know that the summation is between 0 and 2. So A is going to be less than y if and only if A is less than 1, because y is between 0 and 1, and if A is greater than 1, then there is no possibility for A to be less than y. So I'm going to have to check where A is between 0 and 1 in here, as you can see. Now, when A is between 0 and 1, I can just write this integral like this, okay? Just say that, okay, I'm going to integrate y from 0 to A and then A to 1. Why? Because in here, y is less than A in this part, because it's being integrated from 0 to A. But in this part, y is greater than A, because it's being integrated from A to 1. So in this part, this value, this function will yield 0, and it's going to fade away. This one, on the other hand, is going to yield 1, and we're going to use this one and just integrate 1 from A 0 to A, and it's going to give us the result A. Now, in here, this if you could keep up with it, this calculation is actually simple, but this chain of thought getting here isn't that easy. We have to make sure that you can see the critical points. So A being less than or greater than 1. This is a critical point, and if there's a problem with A being less than y, it's going to happen if A is less than 1. Okay. Otherwise, if A is greater than 1, then A cannot be less than 1. But A minus y can be greater than 1. Now, this is the other critical point, the other important situation. If A is greater than 1, let's assume that A is 1.5. If A is 1.5 at that time and y is, I don't know, 0.2, then the difference is 1.3, which is greater than 1, which will yield us 0. So if A is between 1 and 2, then y should start from A minus 1, which is the lowest limit it can be without going to 0, without the f function going to 0. So it has to start from a minus 1 to 1 in this formula. Now here this fx is 1, because if y is the lowest value y can take is a minus 1, then this value is 1 and this fx gives out 1. So in here we know that this is going to give us 1. So all we have to do is just integrate 1 from a minus 1 to 1, which is going to give us 2 minus a. So we have two different PDFs, and we're going to write this as piecewise. So in this piecewise, you can see when a is between 0 and 1, we have an f and PDF of a. When a is between 1 and 2, we have a PDF of 2 minus a. And in other situations, we don't have any value. It's just 0. The PDF is just 0. Now, the same thing for Poisson random variable. Poisson is not, continuous, so it's going to be approached differently. Now, with discrete random variables, what we have to do is just give a value for x plus y. We will just assume that x plus y is n, for example. And then we will say that if x plus y is n, and if x is chi, x is equal to k, then y is going to be equal to n minus k. Now, we know that x and y are independent, and we are looking for this probability, Instead of writing this one, we can just write this one. So, in here, we are looking for all values of k, of course, and we are looking for this probability. Now, in here, we're going to have to check to see, all values from 0 to n, of course, for k. We're going to have to check to see what we can do with these, variables. The thing is, they're independent, so they can just be separated. So we're going to separate them. And we know that they have Poisson random variables, so we can just write e to the power of minus lambda times lambda to the power of k over k factorial. So we're just going to write these parameters, lambda 1 and lambda 2 for these ones, and write those parameters with these k and n minus k values. So as you can see, these are the open formulations we get. Then what we have to do is just simplify them, get them together as much as we can. You can see that the sum is over k, so any value, any term that doesn't have k can be thrown out of the sum, which we're going to do for these e values. And over here, now we have this one. Now, when you take a look at this, this should look familiar. It's not very enduring, but it's familiar. If we add n factorial to this part, then we have to add and divide this part by n factorial as well. We get this one. Now, we have this n factorial, n minus k factorial, and these lambda 1 to the power of k and lambda 2 to the power of n minus k. This is actually very, very, very familiar. It's the, binom açılımı, x artı y üzeri k'nın mesela. It's the, Pascal triangle. You should remember that one as well. So what you have here is lambda 1 plus lambda 2 to the power of n. This one, as you can see. Now, this is equal to this one. This is something you should, just feel, and then, you can check from some place and just write it, of course. But still, we have this one. And these values are over here. Now, as you can see, this final part is actually a Poisson random variable with the parameter lambda 1 plus lambda 2. So when we add two, variables, the total, two Poisson random variables, the sum is again a Poisson random variable, but it just has its parameter grown because the parameters are added to each other as well. Now, we can do this one for binomial random variables as well. So let's say that we have a binomial random variable, two binomial random variables with parameters np and np. They have the same probability, and we're going to try to add x plus y together. Now, when we do that, just as in Poisson random variable, they are again, discrete random variables. So we can just add, a value to the sum. So we're going to just say x plus y is equal to k. And then we're going to have to take apart x and y. So x is equal to I and y is equal to k minus I. And then start from there. We're just going to be, separating these two because they're independent. And then we're going to write the binomial random variable, definitions. And then we're going to just simplify them and we will get this one. This is actually another binomial random variables with parameter p and trial number of n plus m. So two binomial random variables sum together gives us another binomial random variable as well. The thing is, let's go back a bit. Poisson and binomial gave us the same thing, but with uniform it wasn't. With uniform, two uniforms added together actually gave us a triangular shape, a triangle distribution shape. So this one didn't hold. It's not always like that, okay? Summing two same type variables doesn't always yield same type variable once again, okay? Don't condition yourself like that. So as we said condition, we have also conditional distributions in joint form as well. Now, in the discrete case, this is actually very similar to the chapter 3 definition. We again have the same thing. So we can say that x given y. X given y means x equal to x given y is equal to y. Now in here, this is just like the definition in third chapter. We're gonna take the intersection of these two, and we're gonna divide it by the second one, the condition. Now the intersection of these two is their joint PDF or PMF. In this case, it's PMF. It's their joint PMF. So what we write is their joint PMF over here, and this one is just the marginal of y. So the joint formula over the marginal formula. This is the same for every conditional distribution for joint variables, discrete or continuous. Doesn't really matter, but this is what we're going to use. But it's the same, okay? It's just changing a bit. The form is changing a bit, but it's the same thing. Intersection over the condition. Now, as you can see, it's the same for, of course, the CDF as well. We can write it like this, and we can just write it like this over here. It doesn't really matter. And if they are independent of each other, then x given y is equal to x, which was the same with, in the third chapter with just events and stuff. So here's a simple example for the condition. Now we have a pxy, a simple PMF with 4 points. 0 to 0 is equal to 0.4. The probability of being 0 and 0 is equal to 0.4. Probability of 0, 1 is 0.2. Probability of 1 and 0 is 0.1, and probability of 1 and 1 is 0.3. Now we can see that these four probability values add up to 1, so there's no problem in there as well. It's asking us to calculate the conditional probability mass function, conditional PMF, for x, given that y is equal to 1. Now, we have to find the marginal of y, and the value of y is equal to 1. Now, it's simple here, because we're just going to have to sum all the probabilities that have 1 in their, y value, which is this one, 0, 1, and this one, 1, 1. So it has 0.2 and 0.3, so the total is 0.5. This is the margin of y, 0.5, the total margin of y. Now, we need to divide the joint by this one to find each and every one of the, PMF values. We have two of them, 0 given 1 and 1 given 1. For 0 given 1, I have to find 0, 1, like this one, and divide it by the marginal. It's going to give me 0.2 over 0.5, which is 2 over 5, 40%. And for 1 given 1, I have to find the P11, which is 0.3, and divide it by the marginal, which is 0.5. It's going to give us 3 over 5 or 60%. Simple, actually. This part is it. Now, what about the continuous case? In the continuous case, again, the same thing. We have the joint PDF over marginal PDF. It was joint PMF over marginal PMF. Now we have joint PDF over marginal PDF. So it's actually the same thing. The formulation doesn't change, but instead of summation, we're going to use integration now, of course. But still, the rules and the types or the methods are the same. For example, there is one slight important part here that's going to be confusing for you. We know that this is a continuous case, so both x and y are continuous random variables, and we are looking for a probability where the condition is y is equal to y. It's a discrete point. Continuous variable with a discrete point we are talking about. But this is a condition. This is something that has happened. We know that this has happened. So it can be, calculated. It doesn't really matter. It has happened. Okay. Normally we would just say the probability of y is equal to y. This is 0 because y is continuous. Yes. But it's a condition here. Okay. This has happened. we are trying to act according to this one. So we're gonna calculate it and you will see. Now, as you can see here, we have the joint density of x and y. Now, in this one, I'm looking for the condition of y. So first I have to find the marginal of y. I need to find the marginal density of y. To find the marginal density of y, I'm going to have to integrate this one for x, dx from 0 to infinity. So, as you can see here, 0 to infinity, integrate this one. And I'm just going to write the fxy anyway. This one is going to be written here anyway, because it's joint over marginal. So, I'm looking for joint over marginal to find the, conditional x given y. Joint condition. So when we take this integral, there are going to be simplifications, etc. I'm going to get this value. Now this is for x given y, for any x and any y. Okay. Now it's asking me this one. Probability of x is greater than 1, given that y is equal to y. Y is equal to y doesn't change anything right now. It's going to stay like this. But x is greater than 1 means that we have to integrate x from 1 to infinity. So we're going to integrate this one from 1 to infinity, which is going to give us e to the power of 1 minus y. Now it says that whatever y value you choose 0, 1, 2, 3, 5, 4, 6, whatever, it's going to be like this for x given y. You can just plug this y value in here and you'll find the PDF. So we can still see the same thing about independent random variables in the continuous case. They're just going to simplify each other. As you can see, x given y, the conditional joint PDF, is given by joint PDF over marginal PDF. The joint PDF, as they are independent, can be separated and taken into two parts of x and y, and the y's are going to simplify. The x is going to be left here. So x given y is equal to x because it's independent anyway. Now this part is another important subject in this chapter. This is actually using two random variables related to other two random variables, and using those two random variables to formulate a joint random variable, joint PDF for the other two. Now, in here, there's a let's say simple but important things to take care of. It's actually two steps. This one is actually two steps. We're going to have to find the x values in terms of y, and we're going to have to find the Jacobian. You will understand what I'm talking about. Now, this here is g1, x1, x2, and y1 is equal to g2, x1, x2. You can just call y1 and y2 in terms of, just show them in terms of x1 and x2. Now, this here is a Jacobian matrix. Now, we're going to find the, determinant of it anyway. Now, in here, you can see that we are just differentiating y in terms of y1 in terms of x1, and differentiating y1 in terms of x2. And then here, differentiating y2 in terms of x1 and differentiating y2 in terms of x2. The lines, rows, are for y's. The columns are for x's. That's the easiest way to remember. Now, after this differentiation, we find the determinants of the Jacobian over here. Now, you will understand it better in the example slide later, you will see. This over here, this one is actually the most important part, I think. This one over here gives us the joint density of y1 and y2 in terms of joint density of x1 and x2. But those x1 and x2, this is normally a function of x1 and x2, but we're going to change this function into a function of variables y1 and y2. You'll see what I'm talking about in a second. But still, the Jacobian is over here, and Jacobian is taken as the absolute value and -1, power of -1, which is going to give us 1 over Jacobian. Now, start simple. Let's start simple. X and y, x1 and x2 are jointly continuous random variables with probability density function fx1, x2. Now, we don't know the joint density function itself, but it can be anything. They can be anything. So let's leave it at that. But we know that y is equal to x1 plus x2 and y2 is equal to x1 minus x2. So we have to find x1 and x2 in terms of y1 and y2. To do that, I can just add these two values together. So y1 and y2 is equal to 2x1. Then get it to on the other side, x1 is equal to y1 plus y2 over 2. To find the other one, I'm just going to have to subtract these from each other. So we will have y1 minus y2 is equal to 2x2. So I can say that x2 is equal to y1 minus y2 over 2. These are the two transformations we have to make. We have to find x's in terms of y. Then we have to find the Jacobian. Now, to find the Jacobian, we have to differentiate for y on the rows, and for x's on the columns. So differentiating a y1 with respect to x1 is going to give us 1. With respect to x2 is going to give us 1. Differentiating y2 is going to give us 1 and minus 1. So what we have over here, 1, 1, 1 minus 1, the determinant is minus 2. So the Jacobian is minus 2. The Jacobian value is minus 2. What I need is the absolute value and the 1 over value. So it's 1 over 2 actually. I'm going to use 1 over 2, as you can see. And for y1 and y2, we have already found them in terms of x1 and x2. I'm just going to plug these values inside fx1, x2, the joint of x1 and x2. Now this over here, this term over here, is the joint density function of y1 and y2, these two, okay? This over here is the Jacobian plus the joint density of x1 and x2 together. Of course, 1 over absolute Jacobian, what's the? Now, another question. This one is actually a bit, looks more complex, but it isn't really. This one has 3 independent standard normal random variables. And it's going to be, it's going to be transformed into 3 y random variables. They don't have to be normal, of course. They're not going to be normal anyway, for the most part. Now, we have y1 is equal to x1 plus x2 plus x3. y2 is equal to x1 minus x2, and y3 is equal to x1 minus x3. Now, what I need is the Jacobian and transformation formulas. The Jacobian is easy. For y1, we have 1, 1, 1. For y2, we have 1, minus 1, 0. For y3, we have 1, 0, minus 1. So what we have to do is just take the, determinant of this matrix, which is going to give us 3. Now, this is the Jacobian. So at the end, we're going to need 1 over 3. And now we have to transform y and x. So we already know y values in terms of x, but I need x values in terms of y, and it's going to give us this one. x1 is easy. Just multiply all these 3 y values, and you're going to get y1 plus y2 plus y3 is equal to 3x1. So x1 is easy. From there, we can find x2 and x3 as well. Just put it into, into the equation and solve for 2 unknowns, 2 equations, 2 unknowns. Then we're not done yet, because these are the transformations, but these are not the standard normal random variables, not those independent guys, not those let's say joint PDF values. So these are going to be plugged into the joint PDF values. These are not the function itself. So we already know that the joint PDF for x1, x2, x3 is this one. Why? It says standard normal random variable. Standard normal random variable has 0 as mu value, and 1 as standard deviation or variance, doesn't matter, as a mu value. So mu is 1, sigma is 1, and mu is 0. So when we plug those two into the normal distribution, we get this one. Now in here, you can see that we are adding xi squares. So I already know what the x values are in terms of y, these 3 values. So I'm going to add all these squared. So instead of writing this real long equation, we just write q over here. You could have written something else, or you could have written all these terms in here as well. It's okay, it doesn't really matter. It's just for easiness, for easiness of reading. We're just going to plug q over here, and we know that q is equal to this one, this square plus this square plus this square. So this is what we're looking for, how the Jacobian really works.